Down here. Most of these existed in GHC 7.10. The two new ones are Undecidable Superclasses and Type and Type. So I just want to talk about a couple of things that are coming up in GHC 8. And one of them was this little trick that Simon added for me just before Christmas. So I like to think he gave it to me as a Christmas present.
Can you scroll back up a little bit where it's all just language extensions?
Yeah, there you go.
Thanks.
You can just copy the gist.
Yeah, but he wanted the picture of me doing it. All right.
Fair enough.
So the first extension that's interesting, I think, is Type and Type, which is where we start getting the ability to talk about kind classes rather than type classes. We can start doing things with kinds. We can make kind aliases. Star now becomes a synonym for this funny, the type is actually the real thing that's underlying star now. And this is actually capital type, in all scary quotes, lifted, if you fully expand it out. Because there's now a type unlifted and a type lifted to play with. Okay? And that means that I can actually start building my own kinds. I can say, hey, here's a new kind. I'm going to make cat I a type, a kind alias that says I to type. It says I to star. Which you would not normally, you can't say that today in Haskell. This is like the first kind of quirky, like let's just play around with some of the new stuff. And so here's a class vacuous or whatever that takes an argument P of kind I to star and a value A of kind I, and says everything has it. So what I wanted to do was play around with some category theory in Haskell. And the way that I like to talk about category theory in Haskell is a little bit funny. If you look at the kind of arrow, arrow has kind star to star to star, right?
Oh, that. Oh.
The kind of arrow. If you type colon K on that type, you'll get star to star to star.
I thought you were talking about the type class arrow.
And no, just function.
Yeah. Okay.
And so if you look at like the way category theorists like to talk about categories, they like to say, hey, look, we have a hum functor or something like that, which goes from the category for if you have the hum for C is the kind of is the functor that describes how its arrows work. It says, if you give me two objects in the category, I will give you the set of all of the arrows. Okay? So this is one object, a second object in the category, and I will give you the set of all the arrows between the two. Okay? But this being Haskell, this is curried, right? So what it's really saying is if you give me one object, I will give you something that when given another object will give you the set of all arrows between here and there. It's a bit of it's a curried definition rather than going from the product of two kinds to a kind where we've curried this out. So we have this notion of a product kind and all this crazy stuff going around now that we could use. We don't. So what this means is if I want arrow to be the kind of, like the function thing, to be the thing that I build my category on, I need to do all of my hum functors curried. They're a functor from something to another category. So in this case, they're a functor from my category itself, or from the opposite category of my category, to the category of natural transformations from my category to set, which is a mouthful. But we run into a problem, which is that category now requires functor. But then to define a functor, functors go between categories. So we have this notion of undecidable instances today, which lets us make instances that have a cycle in them. Like when you go to define, if you go to like define the instances for monad state or something for a particular monad transformer, you always have to turn on this flag and everybody ignores it and doesn't think too much about it. But it's allowing the potential for there to be a cycle when you go to do instance resolution. Here we're allowing the potential for a cycle when you go to expand all of the superclasses of a class. Okay? So this turns out to iterate out to a fixed point. This actually will expand and expand and expand, but it stops expanding at a certain point. So there winds up being 9 instances that you need in order to make this thing go. But by the time we're done, we can actually say that every category is actually a functor, and that functors go between categories.
So in the compiler, you're going to have to lazily instantiate superclasses.
Actually, the compiler rather eagerly expands them until it finds a fixed point, until nothing new is needed. And then it stops. Okay. So Simon originally panicked when I put this forth to him as an idea. There was on the ticket. He's like, this is too hard. And then he eventually came back with, hey, do these always reach a fixed point? And it looked like the answer was yes. And so he sat down with Demetrius and banged it out over a couple of days.
So what happens if they don't?
Spins forever.
Okay.
Don't do that. So fortunately, this is at the class declaration time, and you have to put all the classes in one file. So it's your fault, and it's your file. So unlike instances which can be put up by anybody, classes that go in a cycle are going to have to live all together. So it's not as bad as it sounds. Okay. But with it, I could, in theory, actually get this file compiled. Unfortunately, there are bugs still. So I tested in the implementation. So in the version that was shipped with GHC 8.0 release candidate 1, this file would spin forever. Then we got release candidate 2, and it spins forever. But it spins forever for a different reason, which is good. And now, if you take head, it doesn't spin forever. It crashes, saying...
Improvement. It's a step.
I was going to show the error, but it says... categories. No match in record selector CTEV_dest. Exception, GHC crash. So, but that's a different bug that we know that in theory is on Richard's plate to get fixed. So, assuming that bug gets fixed, this code should eventually be able to compile. And the whole reason that I'm interested in this is I have a little library that I currently have on Hackage called Hask, which is a bit more it's closer to real category theory. It's still bizarrely broken Haskell-y category theory, but we can actually define a few things that are kind of like the freshman dream of Haskell. One of them is that we can define, a functor for arrow, not arrow, comma, arrow of E. We can define functors for list and maybe, right? They're not too surprising, IO. We can also define the functor for pair, not for pair applied to something, but for pair. Because this maps over the first argument and then returns you a natural transformation, so you're natural in the remaining argument. So you can actually now map over any argument in a pair by removing as many nat constructors as you have to by using the appropriate number of run nat calls. Okay? So you can now be functorial in as many arguments as you need to be. Either is also a functor. Not either A is a functor, but either itself is a functor. Okay? So if you're looking for the sort of standard Scala excuse for why we don't have positional type arguments in Scala, it's because maybe you want to map over the first argument, maybe you want to map over the second argument. Now you can, and we didn't have to give up positional type arguments. But also, the way this gets constructed, the way that I build bifunctors is by just saying that it's a functor that goes to a functor category. Or to build contravariant functors, it's a functor from the opposite category. So contramap here just goes from the opposite category of whatever I come from.
Nice.
and we make one definition.
Does op somehow, is op equals id somehow encoded in here?
Yes, this one uses a trick for that, which is that we require.
What does the tilde mean?
Okay,
That's type equality.
that's type equality. That's saying that the domain of P must be the opposite category of P. And the codomain of P is the category of natural transformations from P to set, or to Haskell. Okay? And then we say that the objects in the opposite category are the same as the objects in our original category. And technically there should be one extra requirement, but I haven't been able to prove that this will actually make it through GHC once we fix that other bug, which that the opposite of P is P. And that collapses everything down. And so the standard definition for op of P is this uneta of P, which is basically, let's flip the arguments around. Woohoo! Let's run the arrows backwards, right? Y of P, AB, is P, BA. So we get our arrows, this just flips our arrows around. It'd be like a dual category here. And then I require a couple of operations. I'll let you go back and forth to the opposite category. Just talk about arrows in the opposite category. And then,
But you have to have two. You have to have op and unop.
yes, you have to give both of these definitions because these put on and take off whatever your encoding of op is.
What's default?
Even though it should be the same.
These are what's called default signatures, which say that if this constraint is, if this type signature on the right-hand side is satisfied, then you don't actually have to write in the body. It will plug it in. And if not, you would have to check. So when you go to make an instance of this thing, if you don't supply target, it will look for this stuff. If it can prove that ob of P is vacuous P, which is that empty constraint that always is satisfied, for instance. If it can prove this is the definition of ob of P, then it will give you this definition. So you don't have to supply target for the vacuous cases. Yes?
I have actually just a question about those default signatures. Can you actually tighten the type part of the type signature when you're making a default signature?
I don't know. I don't think so. You can always do so by taking these things and moving them into equalities on this side. Make extra constraints that A is twiddle something, is something.
What is the?
But that may not work because if this A is parametric, if it's not part of the class, then you can't do that. So
Default signatures are what exactly are they doing? They're
you might want to say that if, I don't know, if your applicative is a monad, then app, the less than star greater than should be equal to app from control monad, right?
okay.
Which would let you avoid having to make that definition. So if you just wrote if you wrote instance applicative and you said pure is something, and you didn't say what app was, if you then had a monad line right below it, that would be okay.
Most common place I see them is using GHC generics.
That's what I use them for, yeah.
Yeah, like if, for example,
Likewise,
JSON
what-
from JSON and serialize. If it can prove generic, then it can implement it for you automatically.
So you're
monad
saying
does, you have to write, when you're defining a monad, you have to write return equals
Pure or something.
Pure, equals pure.
Yeah.
But if you put this in your definition of monad and you wrote pure, you wouldn't have to write return.
Okay, so basically it's saying
Well, since every monad is applicative now, you'd want.
Oh, did we change that?
Yeah.
Good.
if I don't supply this, assume that it's then glue on.
Then look for
additional-
that constraint, and if you
glue on
can't,
it-
complain very, very loudly.
Okay, all right, that's handy.
But you can't define multiple defaults.
No, you're only allowed to put one in. And this forces you to do things like put both this thing and whatever you want this default to trigger off of in the same module. So monad and applicative would have to be defined together in the same module and then maybe exposed to the end user that way, that kind of thing. So here, what I say is
So what
that
would it
the default, this is a way to make a default for a class-associated type. The default definition of op of P is this y of P, which flips the arrow around, right? But since I want op of P to get back to P, then when I go to define the instance of category for Y, which I have to skip past a bunch of other stuff to get to, category for Y of P, then op of Y of P is P. rather than op of p being y of p, right? So this way,
Y, it's not Y of Y of P.
y of y, yeah, op of p gets you back to p if you went through y in the middle.
And one nice thing about this is you have a self-dual category. You can actually make it self-dual, which was not the case with the old version of Haskell.
Yeah, so the new thing here can do things like,
Self-dual means op.
like if I have a category that's, you know, where I have the ability to flip my arrows around, or actually I don't even need that, if I just need it, if it's equal to its, if it's isomorphic, there's an isomorphism of categories between it and its dual category, then here I can say, we have a category of type equalities, right? You have A twiddle equals B, only when A and B are the same type.
Okay.
And then here we can say that the opposite category for the category of type equalities is the category of type equalities. Or the discrete category of Haskell would be another way to talk about this thing. And then say, hey, the identity arrow is REFL, and we can just use trans from that. But since we put it in with the opposite order of dot.
So category has ID op on op.
And here we just say, use the ability to swap these things around, because this one happens to be a group point. And then we need the fact that every category is a functor from its opposite category, which in this case is itself, to the category of natural transformations from itself to set. And this definition is basically forced.
So in this
This
case,
definition is forced, and then we just say that it's
does
group point.
functor degrade somehow in a way that it just so in this case you're writing functor means a functor on two categories.
Yeah, it's a functor from
Whereas
some category to some other
The
category.
functor that currently exists is a functor is
From
an
Hask to
functor.
Hask, always.
Right.
Here my
Is that a
definition of a category is my functor is more
functor.
general. You can have any f that goes from any kind I to any kind j you want, so long as you have a category
I.
on I and a category a category whose objects live in kind I and a category whose objects live in kind j. Then you can take arrows in that first category, 2 arrows in the second category,
And all of our current functors
fit into this mold.
fit into that mold just
With
because
this
they are.
being arrow and this being arrow.
A lot more also fit into that mold.
Yes, a lot of things fit in here now.
Right. But everything that used to still does.
Everything
without
that used to fit can fit into this
Do you-
particular crazy mold.
Do you have to change anything when you define the instance? You have to define those stuff.
You have to define new instances. You have to define instances for my crazy functor. But now you can define those extra instances that weren't possible before.
No way to get the type
No, it doesn't automatically do.
default to.
I can't even do default signatures because I can't make a default signature that limits the kind of this to be star to star to star, which is kind of annoying, actually. I would really like to be able to say, you know, type dom f equals star to star to star, or type dom f equals function arrow, assuming that the kinds match. Because if I could do that, then the amount of work to instantiate this class would be the same amount of work to instantiate the existing functor class, and one could envision that in 15 years, when we can get people to actually care about this stuff, that you could replace the existing functor class with this.
Well, couldn't you get, I mean, it seems like type in type could enable that.
I think it's become possible because we can now talk about kind equalities. It wasn't possible to do before when I brought it up to Richard 3 years ago.
Yeah.
Now it's a thought we can think. So it's a ticket I can file. I think that's a ticket I will file.
There's no way to, these things are actually undecidable. There's no way you can detect when, if I give you a non-terminating system of classes, of cyclic classes.
Well, right now it elaborates for a fixed iteration depth, and you can raise the iteration depth to as high as you want,
That's the typical.
or to infinite.
That's the typical way you handle that stuff.
Yeah, so it's just elaborating to a fixed point, and since you're writing the source file, you can pick the bound as big as you
But
need.
there's no smarter way to make that,
I don't know a universal way to detect if this sort of elaboration process will ever provably terminate.
yeah, you look like you can probably tease first order logic out of this.
Yeah, for me it's like I originally wanted this so that I could talk about, like, if I had a ring, I want to build the field of fractions over that
Right.
ring. And then in Haskell, I want to be able to say that the field of fractions of the field of fractions should be the original field of fractions.
Right.
Like, completing it twice shouldn't take you further out. Or that if you want to build a group, you should be able to say that every group forms a module over the integers. But then modules, you should be defined with a group. So now you have a cycle between module and group. That's where these sort of things
So
start popping up
this
in
is,
math.
so in other words, you're saying this is really handy for anything where you're basically implementing mathematical abstractions.
Yeah, for me it comes up, like my algebra package, I've had this long-standing bug that I've been meaning to fix that needs one of these cycles, for instance.
So if I was building a independently typed language, I probably want this.
Well, if you're building a independently typed language that has type classes that are real, honest-to-God type classes. Yeah, sorry. James.
Well, if you have,
Very few.
actually, if you have a type class that depends on an integer and will either, and its subclasses are depending on if the integer is odd or even, 3 times itself plus 1. Or
Oh, you can encode collats or something, yeah. Fair enough. So yeah, you can probably prove that you can't prove that it terminates with just, using collats.
Infinite sequence, actually.
All right, and then like here we've got things like, so in order to make this thing go, I needed some interesting categories, right? Because I've already got to talk about, there's several categories involved in just defining my first, like to define category. I need the opposite category, so now my categories also involve another category. And technically I should require a category of op p, which is another step in this process.
So wait, the domain is the opposite?
No, the domain, so if I take my category itself, my category hum, as it's usually written for C, is a functor from C-op cross C to set. Okay? So it's contravariant, the hum of my category is a contravariant functor in its first argument, right? You map backwards over the input to a function, you map forwards over the output to a function, right? If you think of it in Haskell terms. In my terms, I have to actually go from C-op to the functor category from C to set. This is the category of natural transformations that go from C to set. But it's a functor from the opposite category to the category of natural transformations from myself.
Every category is a functor.
Every category itself, I'm treating the category, remember we define our categories on what our arrows look like, which are our
Every
hum sets.
category is a functor from dom to nat.
From the opposite domain. Its domain is the opposite category to the category of natural transformations from P to itself. And then I need to be able to define nat. So in order to define my first category, I first also have to define another category, which is the opposite category. So we've already got one cycle looping off between category and category,
And then
right?
functors are defined based on.
Then we have functors, which are defined in terms of categories, but then natural transformations have to be a category.
Of course.
So we've got like 3 little loops kind of all dangling together that all have to iterate out to a fixed point. And fortunately, it turns out it does. So this was the complicated example that I fed Simon that he panicked about, and then fortunately Demetrius talked him down. So I was very happy.
Can we see functor again?
Absolutely.
If no one objects.
Okay, so let's just work through category to get there, right? If you don't mind, I'll take that. So every category has an opposite category. And then I put a type of objects in the category. This lets me talk about sum categories and product categories. So the identity no longer works for all A. It works for any A that inhabits this ob P, where you satisfy this ob P constraint.
Which for Haskell is everything.
Yeah, for Haskell that is ob P is vacuous P. So that just says yes. So it just normally works for everything. And then this lets me compose any arrows.
Standard compass here.
And if I know that, if I have an arrow that goes from A to B, then if I ask for the source, this gives me a proof that the source is an object in my category. That, if I have an arrow from A to B, then A is an object in my category.
What's dict?
Dict is this funny little thing that became possible in 7.6. Well, it became possible in 7.4. It worked in 7.6.
Sure, that makes sense.
And so now we can say, hey, look, a dictionary, this lets me talk about an arbitrary constraint. So constraint can be something like eq int or vacuous P int or something like that.
So P is constrained.
So this lets me talk about the category of constraints. I gave my type classes versus the world talk here a few months ago or a year ago or something like that. And that one talks a great length about the category of constraints, so you can play with that. So now we can get we can get proof to us. If you have one of these things lying around, you can open it up and get a proof that A is an object in this constraint. So now this lets you build PAA and stuff like that. If you have a PAB, you can build the identity on the source or on the target.
P here is the category? No, what is
Yeah,
it?
P is my category.
Why P?
Profunctor, because hom happens to be a profunctor.
As
Sure.
a convenience, if you have a vacuous thing, you can always satisfy it. And if
Yeah,
you do
as a
that-
convenience, if the constraint is just the vacuous constraint, then here it's free. Like you can always satisfy the vacuous constraint. So here it is. You don't need to do anything with your arrows. And you can turn your arrows around. And then we have our functors, which go from whatever the, oops, this code doesn't, this should be dom f ab to cod f fa fb, the version that actually compiles on the other machine actually has this code fully transformed. The one that I managed to paste in the gist.
So you've just written that if the category, so F is a functor, if dom F is a category, but you've defined dom F in the definition for functor.
F tells you what its domain is, right? These are type families off of,
Okay.
and this goes from dom f ab to cod f f of a to f of b. So given f, you can figure out what the domain and codomain are. So normally these will be just normal arrow, the function arrow, the Haskell category. And then I can play games because I need to actually be able to talk about functors that start at some category and end at another category in order to be able to talk about natural transformations. If I want natural transformations from the category like C to D, I need to be able to talk about functors from C to D. Or in this case, I call them P and Q.
Functor of?
Functor of is just this aliasing hack. And so this is the thing that broke GHC like after Simon patched it, right after RC2. So this is the thing that Simon fixed for me most recently.
So functors can go from one category to another.
Yes, functors go from, this is effectively what we're saying. This is the category goes from, this is where it goes to.
Oh.
Right? You take an arrow in the category goes from, to an arrow in the category it's going to.
Right, of course. That's what a functor is, of course.
And then my arrows, my natural transformations are saying that if you tell me two categories, P and Q, right, and F and G have the right kind to be functors from P to Q. So you tell me that, F is functor from P to Q and G is a functor from P to Q. And you tell me that A is an object in P, then I'll give you an arrow in Q from F of A to F of B.
So how long until you can rewrite monad as being a
I already have that. I already have monads or monads in the category of endofunctors. I actually have that as a line of code that compiles in Haskell today. And that's what this is desire. I want this to be able to clean that fact up.
Okay.
So you can actually run that line of code.
So
I'll show you.
So I always heard that, and then I read the definition of monad in Saunders,
Mm-hmm.
and it didn't seem to say anything about
Are you online here?
Yeah, drop the gist stuff.
Monoids.
Oh, yeah. Dirt. So, just to actually make that statement, or prove that statement, tensor compose. Here, I was smart and put all my language fragments on one line.
online.
It just scrolls off to the right forever.
So that no one can take pictures of this.
Yes. But here we can say that if you have a functor, and it's an endofunctor,
Okay.
and M itself is a monoid object with respect to that particular, like the definition of composition,
Wait,
then this is the monad. I just class instance. These are just making an alias. Then return uses that thing and
It runs the
all the
natural-
machinery
it runs ID.
to build an arrow in the domain of M from A to M of A.
Right, of course. Yep.
And then
Bind.
bind says, you give me an arrow from A to M of B, I'll give you one from M of A to M of B. So this line is the claim that a monad is the monad in the category of endofunctors, and this type checking is a very weak proof. Okay, so I can actually run this code today. Well, I can't run it today. I could run it 2 years ago, back before Simon fixed it, or before. Okay, so there used to be this horrible type named any, and it's still a horrible type. But any inhabits every kind. So there's a type named any that inhabits every single kind.
Well, actually, that's not true anymore. Now,
It's still a type. It's just a type family with no. It's a type family that doesn't expand anything.
but a type family is not a type.
Yes. Well, okay. We can play games about whether we want to talk about types and type constructors and other stuff. But it's not a thing that you can hang an instance off of anymore since 7.10. Okay. So in 7.10. I pointed out to Richard this horrible hack that I was using to make new members of every kind, which is that if any inhabits every kind, then the kind Boolean now has 3 inhabitants, right? It has true and false and any.
Wait, it doesn't also have undefined?
No, it's a type.
Oh.
The kind Boolean has types, and the types, you don't have undefined at the type level.
Sure.
But any being a distinguishable member of this type means you can now write instances for any, right? But it's not just that any has that kind. Any also has the kind, I don't know, unit to bool. So any unit, any quote unit, has kind bool. Any has kind nat to bool. So any 0, any 1, any 2, any 3, any 4. Any has kind constraint to bool. So any of each int inhabits bool. Right? No matter what thing you can kind of think of to shove after any, it inhabits whatever kind you want. Right? Because you can just take whatever its kind was and throw it on the list. So the hack that I used to use was this. I would make a new data type, compose,
Is the all
which was with a single constructor, compose.
all caps doesn't mean anything, does it?
This was just to have it different than this one.
Okay.
So now we have capital compose that's inhabited by quote compose. As a kind, this becomes the kind capital compose. And this becomes the type quote compose that inhabits that kind, right? So any inhabits the kind, capital compose goes to I to star, to j to star, to k to star, to j to k, to I to k to star. Or I to k, sorry, no star at the end. Okay? That's the kind that I needed to inhabit. And now I can write instances for this. I showed that to Richard at Hack Boston before GHC7 released, and he fixed it. So now I can't do this anymore.
How much swearing happened before he fixed it?
Much.
But you'll be able to
I won't say by who. In the interest of diplomacy.
But we'll be able to bring it back once you...
No. I can't fix that. But here's my current hack. Okay, so I can't do this anymore. Fine. You win. But what I can do is this. I can make a class-associated type named compose and bake it into my some class, right? And then I just don't ever tell you what the expansion of it is. And if you don't know what the expansion is, you can't expand it, right? I can just make a class-associated, or I can make an empty type family. Now, I can't write instances for this directly, but I can use my horrible reflection library, or the same approach that I used to make my reflection library go, manufacture instances from whole class that should never be able to exist. Okay? So then I can hack the type system to let me make instances for compose as long as I open the appropriate dictionary to bring them into scope. And they would be brought into scope for the unexpandable type family that is compose from category C, D, E, F, and G. And then I can make compose of 2 functors a functor for no matter what category I happen to end in. And it's horrible, and it's wrong. And I don't have to worry about anybody else writing such an instance because they can't. So it actually turns out to be correct.
Weird.
So, so I have a new hack, and I'll play with it later, but I just wanted to show off the fact that undecidable superclasses seems to be coming, and it actually does have some rather interesting uses. Mostly for me, they involve me using it with a whole bunch of other things that are borderline legal in the type system.
Sure. Seems good.
Thank you.
It's a pretty funny track to do.
Hmm?
It's a pretty funny track to do also.
the kind, I love that kind. Composed,
Yeah, how many times did you have to practice saying that before you could say it so fast?
I think that might have been the first or second time I've done it.
So
I
what
don't know.
are IJ and K? Oh,
Those are the kinds for the objects in the individual
I
categories.
personally heard you say that kind at least 5 times.
Okay. Then I have a very, very bad memory.
Sorry about this. The room closed at 9 o'clock.
Oh, by all means, yeah, we'll totally get onto your.